The rate law of many reactions cannot be predicted from the stoichiometry of the overall reaction. For instance, this reaction shown here, C2H5Br plus ammonia, NH3, does not follow a rate law which is first order in C2H5Br and first order in ammonia. In fact, the experimental rate law for this reaction is first order in C2H5Br, and we could not have predicted that based on the overall stoichiometry of the reaction. An explanation for this is that the reaction actually occurs in more than one step. So there are two elementary steps. The first one is reliant only on the C2H5Br, and it falls apart to form a cation and a bromide anion. And then in a second step, the C2H5 cation reacts with the ammonia to form the C2H5 NH2 plus NH plus, and then the H plus and the Br minus combine to form HBr. Notice that these two reactions add up to give us the overall reaction as written above, and that the intermediate that is formed in the first reaction gets used up in the second reaction. When we have a product of a first reaction that's used up in a second reaction, we call that an intermediate. It doesn't show up in the overall reaction. It's only an intermediate species that shows up on the way to making the final product. The two steps that are combined to form the overall reaction are called elementary reactions, and we write these elementary reactions in such a way as to depict what is actually happening on the molecular level. So when we write a series of steps that add up to an overall reaction, we are intending that these elementary steps will depict what is actually occurring on a molecular level. So one of these molecules falls apart to form this cation and this anion. And then these cations that are formed bump into, collide with an ammonia to form the final product and an H+. And then the HBr is formed from the cation and the anion of the two elementary steps. But how is it that this proposal of this mechanism, this two-step mechanism, would help to explain why the experimental rate law is only first order in the C2H5Br? That's the question we want to answer at this point. We can imagine at least two possibilities for this two-step reaction. So possibility number one would be that the first reaction is slow and the second reaction is fast. Alternatively, we could imagine a second possibility where the first reaction is fast and the second reaction is slow. Let's see if we can think through what would be the case for these two possibilities. Starting with the first possibility, if the first reaction is if the first reaction is slow, then we're going to build up, we're going to make some of this intermediate, and we're going to make it fairly slowly. And as soon as this is made, The second reaction is fast, and so as soon as this intermediate is made, it gets used up really quickly in the second reaction. And so what limits how fast we can make this product is this slow reaction, the slow production of this intermediate. So this is analogous to if you have two people who are washing dishes. And let's say that you start with dirty dishes and you're making clean, wet dishes. And then a second person takes those wet dishes and dries them, so you end up with dry dishes at the end. So the overall process is dirty dishes go to clean, dry dishes. If the person who is washing the dishes is really slow, then the person who's drying the dishes can easily keep up with the amount of wet dishes that are showing up in the assembly line. So you end up with the dry dishes being made as fast as you can make this intermediate. And therefore, this first reaction determines the rate of the overall reaction. And so the slow step is the rate determining step, the step that determines how fast the overall reaction can happen. Let's think about the second possibility. In the second possibility, the person who's washing the dishes does it really fast, and the person who's drying the dishes is really, really slow. And so the wet dishes start to accumulate and build up and build up and build up, and the person drying the dishes can't keep up, and so you keep making more intermediate, and it only gets used up very slowly. And so the rate at which you can make these dry dishes tends to depend more on this second reaction. It depends more on this slow reaction. So in general, the slow reaction is the one that determines how fast the overall reaction can go. So it determines the rate of the overall reaction. So we call that the rate determining step. When we have elementary steps, since we're describing what happens on a molecular level, we can use the stoichiometry of the elementary step to predict the rate of a given elementary step. And so we would predict that the rate of the first step in this mechanism would be some rate constant for the first step times the concentration of C2H5Br to the first power, because the stoichiometry of this elementary step is just one of these C2H5Brs. However, the rate of the second step in this mechanism we would predict to be equal to some rate constant for the second step times the concentration of the intermediate times the concentration of the NH3, because this second step involves a collision between the C2H5 and the NH3, and this reaction can only happen as fast as that collision happens, and the probability that that collision happens is proportional to the product of the concentrations. And so we can see that since the experimental rate law is first order in C2H5Br and does not involve the ammonia, that in fact that first step must be the slow step, and this first possibility is the one that matches with our overall rate law. Finally, each of these steps in the mechanism have their own rates and their own activation barriers. And so we can draw an energy profile for this reaction, knowing that the first step is the slow step and the second step is the fast step. We know that the activation barrier for the first step is larger than the activation barrier for the second step. And so we have reactants starting out at their lowest energy configuration. We form a transition state or a high energy complex for the first reaction, and then we form the intermediates in their lowest energy state. And then we end up going over another hill when we react the intermediate with the NH3, so that has its own activation barrier, which then produces the products in their most stable states.